So you know how there's never anything good on TV? Like all you ever see is some really handsome guy up at Crater Lake, or some super athletic dude doing belly flops, or an awesome dog catching snowballs. Well, you're in luck, because I got this idea for a new reality show. What I want to do is take 6 single men and 6 single women and pair them up, and then send them to 6 different remote corners of the globe. Beautiful outdoor places, secluded coastlines, snowy mountaintops, dense lush jungles. You get the point. It'll be a first date like none other as they work together to survive in these harsh climates. And you're like, wait, I thought this was a math question. Don't worry, it always turns into a math question. Anyways, with my little dating show, there's going to be a twist. It's hard to keep track of 12 different people, so instead I'm going to use 6 pairs of brothers and sisters. We got Amari and Alice, Blake and Bethany, Charles and Christina, Draymond and Denise, Elizabeth and Eric, and Frank and Felicia. What I want to know is, if the producers decide to just randomly pair up the 6 males with the 6 females, what's the probability that nobody will get paired with their sibling? Because no one's trying to go on a date with their brother or sister. So for example, if we kind of isolated all the males, we could take all the females and sort of shift them down one to avoid any sibling couples. Or instead, we could switch the first 2 and then switch the next 2 and then switch the last 2. But we wouldn't want to do this same switching idea and then shift them down, because doing so would result in some sibling couples. To figure out this probability, we'll have to figure out the total number of ways we can pair up the couples ignoring our restriction, which will be really easy. And then the total number of ways we can pair up the couples without having anybody date their sister, which will be quite a bit harder. Another way to state that second question is, how many ways can we rearrange the 6 female names so that none of them end up where they started out, namely paired up with their brother? That's a famous mathematical question. It's called the question of derangements, and it's a pretty neat subject that you can look into. We'll just scratch the surface in this video. Most people, myself included, when they first see this problem, think that it's something that you could handle by considering different cases. And it turns out you can, but there's a little trick to it. And if you don't see the trick, it gets really ugly. Like for example, if we start with Amari, there's 5 different choices of who could get paired up with Amari, because there's 6 females, but one of them is his sister. But then consider Blake. The number of possible females that he could be paired up with depends. If Amari was paired up with Bethany, that leaves 5 choices for who Blake could be paired with. But if Amari was paired with Christina, for example, then there's only 4 choices left for who Blake could get paired with. And it gets even worse when you try to figure out the number of women with whom Charles could be paired, because that's dependent upon both who Amari gets paired with and who Blake gets paired with. And the further you go down the line, the more complicated this becomes. I'm not saying that you can't solve the problem this way. I'm just saying that there's probably a better way to do it. Maybe we should ask an expert.
Using inclusion and exclusion is easiest, but recursion will get you there faster.
Nice, the rare double hint from Hector. So we have 2 different ways we can solve this problem, and I'm going to do them both ways. Let's start with the easier of the 2, the principle of inclusion and exclusion. What that is a pretty powerful method for figuring out how many elements are in the union of sets. Okay, that sounds like I'm getting a little too technical. Suppose you want to know how many kids are playing sports at your school. Your school only offers 2 sports, archery and basketball. You know that 50 kids are doing archery and 100 kids are doing basketball. So does that mean 150 kids are playing sports? No, not necessarily, because some of those kids might be doing both sports. So if you wanted to know the number of kids playing sports at this school, you'd add up the number of kids doing archery and the number of kids doing basketball, but then you'd have to subtract the number of kids doing both sports, because they got double counted. Here's a shorthand way we can write that mathematically that's close enough to correct for our purposes. Okay, but what if there were 3 sports? Archery, basketball, and cricket, sure. Well, you could count the kids playing archery, count the kids playing basketball, count the kids playing cricket. But again, any kids doing archery and basketball, you're double counting. So you'd have to subtract out the kids doing archery and basketball. Similarly, you'd have to subtract out the kids doing basketball and cricket, and the kids doing archery and cricket. But now we have another problem. Think about a kid that's playing all 3 sports. We initially counted him 3 times when we counted archery, basketball, and cricket. But then we subtracted him 3 times when we subtracted the kids playing 2 sports. So now we'd have to add him back in. Can you sort of see the pattern? You start by including everyone who plays 1 sport, but then you end up overcounting, so you have to exclude everybody who plays 2 sports. But then you end up undercounting, so you have to go back and include anybody who plays 3 sports. The 4-sport case would be almost the same. Add up the number of people playing each of the individual 4 sports, then subtract out all of the people playing any pair of the 4 sports, then add back in any people playing any 3 of the 4 sports, then finally subtract out anybody playing all 4 sports. You alternate including and excluding, hence the name. So how can we apply this to our problem? Well, we could count the total number of ways in which somebody would end up on a date with their sister. That sounds weird. If we start by just counting how many ways Alice and Amari can end up together, ignoring all else, then adding the number of ways that Blake and Bethany can end up together, then Charles and Christina, then Draymond and Denise, then Eric and Elizabeth, then Frank and Felicia. But there's a problem with that. This will overcount a scenario where, for example, Alice and Amari end up together and Blake and Bethany end up together. So we need to subtract out any such situation. And not just for these two pair of siblings, but for any two pair of siblings. But now we're undercounting the situation where 3 of our males get matched with their sibling. So we need to add all of those back in. But now we're overcounting the situation where 4 guys get matched with their sister. So we subtract those back out. But unfortunately, that leaves us in a case where we're undercounting situations where 5 males get matched with their sister. Add those back in. But then finally, we're overcounting the case where all 6 males get matched with their sister, so we subtract that out. This principle of inclusion and exclusion will allow us to figure out the total number of ways where anybody ends up on a date with their sister. And you're like, whoa, you just filled up a whole page with symbols. This is going to be super hard. It's really not as bad as it looks. Let's start from the start and figure out A, the total number of ways that Amari can end up with Alice, ignoring all other restrictions. Well, if we pair Amari with Alice, that'll leave us with 5 choices of the female with whom Blake will get paired. Remember, we're ignoring all restrictions so we don't have to exclude his sister. No matter who we choose, we'll have 4 choices left over for Charles, and then 3 for Draymond, 2 for Eric, and 1 for Frank. So there are 5 times 4 times 3 times 2 times 1, or 5 factorial ways in which Amari can get paired with Alice. But there's nothing special about pairing Amari and Alice. We could have started by pairing Blake and Bethany. Then there'd be 5 choices for Amari, 4 for Charles, 3 for Draymond, 2 for Eric, and 1 for Frank. What I'm saying is that B is also 5 factorial, as are C, D, E, and F. Couple comments here. First, because we were figuring out B, Blake had to be paired with Bethany. If you're really clever, you might notice that this specific configuration that was shown as one of the options that make up the 5 factorial options of B would also be included as one of the options that make up the 5 factorial options of A. It's getting double counted, but that's okay, it's supposed to. Just like the athlete that did archery and basketball initially got double counted, it's okay. We'll make up for that double counting by excluding one of them. Second comment, that only figured out the first row of this huge page of symbols, but that's okay. What you'll see are future rows are even easier than that first row. For example, let's consider A intersect B, the number of ways in which Amari can be paired with Alice and Blake can be paired with Bethany. Well, if we specify these 2 outcomes, then there are only 4 options left for Charles, 3 for Draymond, 2 for Eric, and 1 for Frank. So there are 4 factorial ways in which Amari can be paired with Alice and Blake can be paired with Bethany. And just like we saw in the first row, there's nothing special about picking these 2 pair of siblings. If we pick any 2 pair of siblings, there'll be 4 factorial ways in which we can match the remaining females to the remaining males. What I'm saying is each one of these 15 symbols is equal to 4 factorial. Can you see the pattern here? For each of the terms in the next group, we're picking 3 of the males and pairing them up with their sister. So for example, B intersect C intersect E will represent the number of ways in which Blake and Bethany, Charles and Christina, and Eric and Elizabeth all get paired up together. With these 3 outcomes specified, we can do the same counting argument that we did before. We have 3 females left to choose for Amari, leaving 2 for Draymond and 1 for Frank. So the cardinality of B intersect C intersect E, in other words, the number of ways in which we can pair the couples, guaranteeing that Blake, Charles, and Eric each get paired with their sisters, is 3 factorial. And that's true for any of the 20 terms in this group. In the next group, we're specifying that 4 of the males get paired with their sister, leaving 2 choices for the 5th male and 1 for the 6th male. So whenever we specify 4 of the outcomes, we're left with 2 factorial ways to make our choices. Same idea if you specify 5 of the couples, you'd have 1 factorial way. And when you specify all 6 of the couples, you have 0 factorial ways. It's worth pointing out that 0 factorial is defined to be equal to 1, which makes sense because there's only one way in which we can specify all 6 of the couples. Another comment, I remember thinking it was really weird that we had 6 different ways that we could specify 5 of the couples, because it kind of felt like they were all the same. If you specify 5 brothers are with their sister, well then you're only left with the 1 brother and 1 sister who are forced to get paired up. But don't worry, even though that's a little bit counterintuitive, it's what we want to do to make sure the inclusion and exclusion counts every scenario exactly once. Okay, so we're done, right? I mean, just evaluate a bunch of factorials and then add and subtract a whole bunch of numbers. Well, yeah, I guess you could. The only problem there was that it was kind of tedious to enumerate all the different possibilities. It would be nice if there was a way to figure out how many of each different type of factorial there was without going through the process of listing them all. Well, conveniently there is. Think about where those 5 factorials came from. Those were the ways we could allocate the remaining females to the remaining males if we chose one of the 6 males to be paired with his sister. How many ways can you choose one from a group of 6? Well, if you're familiar with combinations, you might recognize this formula. And yeah, in this specific case, the answer is pretty obvious. It's just 6. You don't need the formula. But writing in terms of the formula will be really useful for future terms. The 4 factorials came when we chose 2 of the 6 males to be paired with their sisters. There's 6 choose 2 ways to do that. The 3 factorials came from allocating the remaining people after we chose 3 of the 6 males to be paired with their sister. So there's 6 choose 3 ways for that. For the 2 factorials, we need to choose 4 of the 6 males to be paired with their sisters. For the 1 factorials, we need to choose 5 of the 6 males. And the 0 factorials came when we chose all 6 of the 6 males to be paired with their sister. If we rewrite these expressions in terms of factorial, some stuff will cancel out pretty nicely. So there's 455 ways in which at least one of the pairs of siblings ends up together. We wanted to know the probability that no siblings end up together. So since there's 6 factorial or 720 total ways we can pair up the males and the females, there's 720 minus 455 or 265 ways in which nobody ends up with their sister. Divide that by the 720 total ways we can pair up the couples, and we get the probability that nobody ends up with their sister. And you're like, oh, cool, that fraction reduces to 53/144ths, which when rounded to 4 decimal places is 0.3681. That's curiously close to the reciprocal of Euler's number, which when rounded to 4 decimal places is 0.3679. Yeah, that is cool, and it's not a coincidence. In fact, if you use factorials to write an expression for the number of derangements that we had, and you know the Taylor series expansion of e to the x, you might be able to plug in x equals -1 and see some similarities. A little bit more on that later, but I'm already 12 minutes into this video, and I still have to show you another way to solve this problem, because it's a lot cooler than the one I just showed you. So I guess I'll have to save the connection between Euler's number and derangements for another video. So remember, our goal was to figure out the probability that nobody dates their sister. And the way we figured that out is we counted how many ways we could pair up the different couples having nobody date their sister, and divided by the total number of ways we could pair up the couples. And it was that numerator, which is the derangement on a set of 6 elements, that was so problematic. We figured out that 265 by taking the total number of ways we could pair up the couples and subtracting all the bad pairings where at least one person was paired with their sister. Those bad pairings were a headache, and we had to use inclusion exclusion to figure out that count, but it got us there. But man, it would be really nice if we could figure this out more directly. If we could directly calculate how many ways there are in which nobody ends up with their sister. And it turns out there is. What we're going to do is consider 2 different cases. And somewhat surprisingly, it's all going to come down to who the brother of the female that Amari gets paired with. Wait, what? Okay, there's 5 choices for the female with whom Amari can be paired because he can't be paired with his sister Alice. Let's just arbitrarily say he gets paired with, I don't know, Denise. Fine. But that's just for visualization. This same logic will work if he's paired with any of the 5 females. The way we're going to figure out whether we're in case 1 or case 2 is by looking at Draymond, Denise's brother. One of 2 things can happen with Draymond. Either he can be paired with Alice, or he can be paired with one of the remaining 4 females. We'll call the situation where he gets paired with Alice case 1, and the case where he ends up with somebody else's sister, case 2. Take a closer look at case 1. What we have are 4 males and 4 females left to be paired up, and these 8 people are comprised of 4 brother-sister pair. It's the exact same question we started with, except instead of having to make 6 couples, we need to make 4 couples. If we're in case 1, the number of ways we can pair up the remaining couples is just the number of derangements of 4 elements. Okay, but what if we're in case 2? Well, in case 2, we have 5 males and 5 females. 4 of the males, Blake, Charles, Eric, and Frank in this case, have their sister still around, who they can't be paired with. And the remaining male, Draymond, has Alice with whom he can't be paired. Because if he was paired with Alice, we would have been in case 1. What I'm saying is we have 5 males and 5 females, and for each of the 5 males, there's exactly 1 female with whom they can't be paired. It's the exact same question, except instead of having 6 or 4 couples, we have 5 couples. And Alice, loosely speaking, is playing the role of Draymond's sister. So the number of ways we can allocate the females to the males in case 2 is just the number of derangements on 5 elements. Since we have to be in either case 1 or case 2, what we've done is defined the number of derangements on 6 elements in terms of the number of derangements on 5 and 4 elements. And importantly, there's nothing special about starting with 6 elements. We could have done this exact same argument for any number of elements. What I'm saying is we can recursively define the number of derangements on n elements in terms of the number of derangements of n minus 2 elements and the number of derangements of n minus 1 elements. This will not only allow us to solve the question that was asked in this video, but any question of derangements. Kinda cool. Want to see it in action? I mean, I guess of course you do because you're still watching after 15 minutes. Sorry about the length. Let's figure out the number of derangements of one element. So now we only have one brother-sister pair, Amari and Alice, and the question is, how many ways can we rearrange the females so that nobody ends up dating their sister? Well, none. If you only have one brother and one sister, you can't rearrange them. Alice is stuck with Amari. The number of derangements of one element is 0. What if you had two elements? So now we have Amari and Alice and Blake and Bethany. How many ways can we rearrange the females so that nobody ends up with their sister? Just one. We could swap Alice and Bethany so that Amari gets paired with Bethany and Blake gets paired with Alice. So the number of derangements on two elements is just 1. With this information, we can use our recursion formula to fill out the rest of our table. If n equals 3, we get the number of derangements of 3 people is just 2 times the sum of the number of derangements of 1 person and the number of derangements of 2 people. So 2 times 0 plus 1, or 2. Similarly, the number of derangements of 4 people would just be 3 times the sum of the number of derangements of 2 and 3 people. 3 times 1 plus 2 gives us 9. In this same fashion, we see that the number of derangements of 5 and 6 people are 44 and 265 respectively. This 265 divided by 6 factorial gives us the same probability that we found earlier, except this time without having to use the inclusion-exclusion method. One last comment before I get to the challenge question. Earlier, we noticed that 265 divided by 720 was pretty close to 1 over e. Put differently, the number of derangements on 6 elements divided by 6 factorial is approximately 1 over e. If we rearrange the terms to isolate the number of derangements of 6 elements, we see that it's pretty close to 6 factorial divided by e. In fact, if we round 6 factorial divided by e to the nearest whole number, we get exactly the number of derangements on 6 elements. That's kind of cool. Well, it turns out that this algorithm for figuring out the number of derangements isn't specific to 6. It holds true for any value of n greater than or equal to 1. It's pretty wild that something as challenging to figure out as the number of derangements can be calculated immediately if we just round to the nearest whole number using this formula. I think that's wild. Okay, on to the challenge question. My show runs, it's a wild success, makes millions of dollars, so there's a huge wrap party for the cast. Unfortunately, Frank and Felicia couldn't make it. If the remaining 10 contestants are sat at a round table where males and females alternate around the circle, what is the probability that nobody sits next to their sister? If you have any thoughts, questions, or solutions, throw them in the comment section.